In July 2025, astronomers turned the world's most powerful space telescopes toward a visitor from beyond our solar system. Hubble and the James Webb Space Telescope captured some of the sharpest images and most detailed spectra ever taken of the interstellar comet known as 3I Atlas. At first, excitement ran high. The comet's activity was unusual from the start. Its coma, the cloud of gas and dust surrounding its nucleus, expanded at an extraordinary rate, quickly reaching hundreds of thousands of kilometers across. Amateur observers reported a strange green tint in the glow, hinting at chemical processes rarely seen in comets entering our inner solar system for the first time. But then something unexpected happened. Just as the comet's most dramatic features were emerging, official updates from NASA and other space agencies went silent. No new headline images, no fresh spectra, and no detailed announcements about the comet's chemical composition. For astronomers and space enthusiasts tracking 3I Atlas, this sudden blackout was jarring. Questions began to mount. Why had the flow of information stopped so abruptly? Was it a technical issue, a matter of safety, or was there something more unusual about this comet that warranted caution? The absence of real-time data created a vacuum. The scientific community and the public were left to speculate about the comet's true nature. Meanwhile, online discussions exploded with theories, some reasonable, some far more sensational, as everyone tried to fill the gaps left by the silence of the flagship telescopes. Despite the lack of official information, one thing was clear. 3I Atlas was not behaving like any comet astronomers had seen before, and the blackout of data only deepened the mystery. The story of 3I Atlas unfolds like a cosmic detective case, with each telescope providing a crucial piece of the puzzle. On July 21, 2025, the Hubble Space Telescope locked onto the comet and captured the sharpest images yet of this interstellar visitor. For the first time, astronomers could study the comet's nucleus, estimated to be just a few kilometers across, and the massive coma of gas and dust surrounding it. These images revealed a dynamic object, far larger and more active than many expected. Just a couple of weeks later, on August 6th, the James Webb Space Telescope took its turn. Using its powerful NEOSPEC instrument, JWST began gathering spectra that could reveal the chemical composition of the comet's coma. The initial reports hinted at unusual activity, but unlike Hubble's visually striking images, JWST released only preliminary technical notes and comments. There were no dramatic photos to share with the public, only the promise that detailed analysis was underway behind the scenes. On August 27th, Gemini South joined the campaign, capturing new images that confirmed Hubble's observations and tracked the evolution of the comet's tail. These data were publicly archived by early September, giving astronomers and amateur skywatchers another chance to examine the growing coma and shifting dust features. Each release sparked online discussions and excitement, but something began to change. After September 22nd, the pace of new observations slowed dramatically. The steady stream of images and data that had characterized the comet's early weeks fell into long gaps, leaving observers waiting and wondering. The silence was noticeable, and for those following 3I Atlas closely, it raised urgent questions about what was happening behind the scenes and why the data had become so sparse. Observing a comet like 3I Atlas isn't as simple as pointing a telescope and taking a picture. Both Hubble and the James Webb Space Telescope operate under strict technical rules to protect their delicate instruments. Hubble, for example, cannot observe any target that comes closer than 50 degrees to the Sun. This restriction is not arbitrary. Pointing too close to the Sun risks stray sunlight entering the telescope, which could damage the sensitive optics and detectors. JWST, with its massive sun shield and ultra-sensitive infrared instruments, is even more constrained. It enforces an 85-degree minimum separation from the Sun, a rule baked into the spacecraft's planning and safety systems. If a target drifts too close to the Sun, the software automatically blocks observations. Attempting to override this safety feature would trigger emergency shutdowns and could even pause all ongoing science operations. These rules are hardwired into the system, leaving no room for negotiation, even urgent observations of unusual targets like 3I Atlas. As the comet traveled along its interstellar path, the angle between it, Earth, and the Sun gradually shrank. By late August, it had moved inside Hubble's 50-degree limit, and shortly after JWST's near-spec observations in early August, the comet also crossed JWST's 85-degree threshold. At that point, both telescopes entered a forced blackout. The science teams at the Space Telescope Science Institute had no choice but to pause, waiting for the orbital geometry to shift again. For 3I Atlas, this means no new high-resolution images or spectra will be possible until early December, when the comet's angle from the Sun opens up again. This technical limitation is crucial to understand. The silence of the flagship observatories is not a matter of secrecy or delay, it is a safety measure built into the design of these telescopes. Every image and spectrum must wait until the instruments can safely observe the comet again, preserving both the spacecraft and the integrity of the science. The early observations of 3I Atlas revealed a comet that defied expectations. Hubble's July images showed not just a nucleus a few kilometers across, but an enormous coma stretching nearly 348,000 kilometers, more than a quarter of the Sun's diameter. This is far larger than what astronomers typically see at this distance from the Sun, immediately signaling that 3I Atlas was unusual. The coma was not uniform. Observers noted shifting dust features and a sunward plume, a bright stream of material pointing toward the Sun. Night-to-night variations suggested that the comet's surface was actively ejecting material, or that the appearance of the plume changed depending on viewing geometry. This kind of activity is rare for a comet making its first pass through the inner solar system. Spectroscopic hints added another layer of intrigue. Early reports suggested a possible carbon dioxide dominance in the coma, which would be highly unusual. Most local comets at similar distances are water ice dominated, so a CO2-rich composition could provide new insights into the chemical makeup of interstellar objects. While no peer-reviewed spectrum confirming this had been released by late September, the hints were enough to excite both professional and amateur astronomers. Adding to the mystery, the comet exhibited a distinct greenish tint. Amateur astronomers reported that this color was unusually persistent and bright, possibly arising from molecules like diatomic carbon or cyanogen. Combined, these features, gigantic coma, dynamic dust structures, sunward plume, and unusual chemistry, paint a picture of a comet unlike any previously observed, and one that demands careful, ongoing observation. While the flagship space telescopes were forced into a blackout, amateur astronomers around the world stepped up, becoming the primary eyes on 3I Atlas. Using backyard telescopes and small observatories, these dedicated observers tracked the comet's changing brightness and unusual color. Many reported a persistent greenish hue in the coma, likely caused by molecules such as diatomic carbon or cyanogen, though it appeared brighter and more vivid than in typical comets. The variations in brightness were another critical clue. Observers noted rapid changes, sometimes shifting by more than a full magnitude from night to night. While part of this scatter was due to differences in equipment and observation conditions, some of it likely reflected real, dynamic changes in the comet's nucleus and surrounding coma. These ground-based reports provided an invaluable window into the comet's activity during the period when Hubble, JWST, and Gemini South could not safely observe it. This citizen science effort also sparked a global conversation online. Social media threads were filled with shared images, photometry data, and real-time discussion. Amateur astronomers cross-checked each other's findings, raising questions about the comet's behavior, color, and tail evolution. In many ways, these observers became essential contributors to the scientific understanding of 3I Atlas, filling in gaps and keeping the broader community engaged while the flagship observatories waited for the comet to move away from the sun's glare. Their efforts demonstrate how even in the era of billion-dollar space telescopes, dedicated amateur astronomers can play a pivotal role in tracking the universe's rarest visitors. The journey from telescope to public release is far from instantaneous. Every image and spectrum captured by Hubble or JWST enters a complex multi-stage data pipeline designed to ensure accuracy and reliability. Raw data first arrive on the ground accompanied by spacecraft telemetry. From there, they undergo careful calibration. Cosmic rays are removed, detector quirks are corrected, and background light is subtracted. For JWST, this process is even more intricate, with multiple stages including detector-level corrections, instrument calibration, and advanced processing to remove artifacts and coad exposures. Each step is scrutinized by instrument teams to avoid misinterpretation of the data. Once the data reach a science-ready state, they enter a proprietary period. For most Hubble programs, this lasts 6 months, while JWST can hold data for up to a year. During this time, the principal investigators, the scientists who proposed and won the observing time, have exclusive access to analyze and interpret the results. The idea is to reward those who designed and secured the observations, allowing them to verify findings before public release. This stage can significantly slow down the availability of data, particularly for high-profile targets like 3I Atlas. The teams must cross-check every pixel, confirm chemical signatures, and ensure that nothing is misrepresented. Releasing results too early could lead to incorrect conclusions, public confusion, or even the need for a formal correction later. While frustrating for the public and amateur astronomers eager for updates, this careful process is a cornerstone of scientific integrity, ensuring that when data are finally shared, they are as accurate and reliable as possible. Even after the raw and calibrated data are ready, they are far from immediately public. Observations of high-profile targets like 3I Atlas undergo extensive institutional review and coordination. Multiple agencies, including NASA, ESA, and sometimes the Canadian Space Agency, weigh in to ensure that the findings are scientifically accurate, legally sound, and properly communicated. Every press release, image, or announcement passes through these layers of review. This process is especially important for interstellar objects, where premature or inaccurate claims could ripple across the scientific community and the media. Every headline is checked, every statement vetted, and every image examined for clarity and context. Press officers coordinate timing to ensure that releases are consistent across agencies and avoid confusion or misinterpretation. Even a routine data set can sit for weeks, waiting for sign-off from project scientists, communications teams, and legal reviewers. For 3I Atlas, these institutional routines compounded existing delays caused by technical constraints and data processing. The result is a slow, uneven flow of information. While the public and amateur observers are eager for updates, the agencies are moving deliberately, prioritizing accuracy over speed. The frustration and speculation that arise from this delay are not a reflection of secrecy, but of a meticulous process designed to get the science right before it reaches the world. As the weeks passed without new images or spectra from the flagship telescopes, speculation around 3I Atlas began to grow. Social media threads, astronomy forums, and online communities buzzed with theories trying to fill the information gap. Some suggested that the blackout was deliberate, perhaps to hide classified imagery captured by military or intelligence satellites. Others wondered if the agencies were withholding data to prevent public panic over an interstellar anomaly with unusual chemical signatures. Scarcity of official information created fertile ground for speculation. Amateur astronomers shared their own observations and images, comparing notes on brightness, color, and tail morphology, but the lack of authoritative updates left many questions unanswered. Even minor anomalies were amplified online, leading to a swirl of rumors and dramatic theories. The discussions often focused on the comet's persistent green tint, its sprawling coma, and reports of a sunward plume, all unusual features that fueled both curiosity and concern. Engagement peaked whenever Gemini South released even limited data. The rare drops of new information sent excitement through online communities, spiking social media interactions to levels 10 times higher than for typical comets. Each release became an event, with observers and enthusiasts dissecting every pixel for clues. Yet, as the gaps between updates stretched on, frustration grew. People felt like they were chasing a ghost, struggling to understand the comet's behavior in real time. The truth is far less sensational than some of the rumors suggest. The slow release is not about hiding secrets or managing a story. It's the result of carefully orchestrated procedures, technical limitations, and the need for scientific accuracy. But from the perspective of those waiting on the ground, the silence feels personal. Every day without new data amplifies uncertainty, turning routine procedural caution into a source of anxiety and fueling a cycle of speculation that shows no signs of slowing. The story of 3I Atlas is far from over. After its close pass by Mars, the comet will continue its journey toward perihelion, which is expected around October 29 or 30, 2025. At that point, it will pass approximately 1.36 astronomical units from the Sun. While this is not close enough to classify 3I Atlas as a classic sun-grazing comet, the rapid heating and high velocity will still place significant stress on its nucleus. Observers should pay close attention to the comet's light curve during this period. Sharp spikes or sudden changes in brightness could indicate surface fragmentation, outbursts, or volatile release, while a smooth curve would suggest steady activity. Another feature to track is the anti-tail, the sunward-pointing spike seen in wide-field images. Its orientation and prominence can shift depending on the Earth's relative position to the comet's orbital plane. Around perihelion, the anti-tail is expected to peak, then fade quickly as the geometry changes. Monitoring this feature can help confirm orbital parameters and reveal details about dust behavior. Color changes are also important. If the greenish tint observed by amateur astronomers diminishes or shifts after perihelion, it could indicate the depletion of certain surface ices or the exposure of fresh material. However, only spectroscopy can confirm what molecules are actually present, emphasizing the need for careful analysis. Once the comet's solar elongation increases in December, flagship telescopes like Hubble and JWST will regain access. High-resolution imaging and spectroscopy will provide the first detailed views since the blackout began. Looking further ahead to 2026, a favorable alignment with Jupiter could create another observational window if 3I Atlas survives its solar encounter. For now, the global astronomy community, professionals and amateurs alike, must work together. By comparing images across dates, analyzing photometry, and questioning dramatic claims, observers can track the comet's evolution even in the absence of immediate flagship data. The story of 3I Atlas is ongoing, and each new observation will turn another page in our understanding of this rare interstellar visitor. As 3I Atlas continues its journey through the inner solar system, the next major milestone will be its perihelion, expected on October 29 or 30, 2025. At this point, the comet will pass about 1.36 astronomical units from the Sun. While not a classic sun-grazing trajectory, the rapid heating and high velocity will place significant stress on its nucleus. Observers should pay close attention to the comet's light curve during this period. Sharp, short-lived jumps in brightness could indicate surface fragmentation or sudden outbursts, while a steady rise and fall would suggest more uniform volatile release. Tracking these patterns over multiple nights is key to distinguishing real events from observational noise. Another feature to watch is the anti-tail, the sunward-pointing spike that appears in wide-field images. Its orientation and prominence change as Earth moves relative to the comet's orbital plane. Near perihelion, the anti-tail is expected to be at its peak before fading quickly in December as the geometry shifts. Observing this behavior can provide valuable insight into the comet's orbital details and the distribution of dust in its coma. Color changes are equally important. If the greenish hue noted by amateur observers fades or shifts, it may signal the depletion of certain surface ices or the exposure of fresh material. However, only spectroscopy can confirm the specific molecules responsible, emphasizing that images alone can be misleading. By December, as the comet's solar elongation increases, flagship telescopes like Hubble and JWST will regain access, allowing a new wave of high-resolution images and spectra. This next round of observations will provide critical confirmation of the comet's composition, activity, and structural evolution. Until then, the global community of professional and amateur astronomers will continue to monitor light curves, anti-tail orientation and color changes, bridging the gap until the next official data release. The story of Three-Eye Atlas is far from over, and each new observation brings us closer to understanding one of the rarest visitors ever seen in our solar system.